All right. Hi, I'm Randy Becker with Keysight Technologies. I'm here at Mobile World Congress Edition 2025. Keysight's helping connect and secure the world. As part of that connecting, we're showing here is our demo MIMO from FR1 to FR3, which is going to be important for 5G and obviously going into 6G. We're showcasing here one of Keysight's newest products from Anapico, or from a company we acquired, which is Anapico. One of their products here, a 4-channel vector source. We've paired that with our MXR oscilloscope, which is used as the digitizer, where we capture, down convert, and then we do the analysis on the VSA software. To start, we'll look here at the software we're using to create these MIMO signals. We have our pathway of signal generation software. We're generating a number of different users in a 5G new radio signal. We have a combination of some single layer beamform signals, both in the minus 60 degree direction and the plus 30 degree direction, as well as a 4-layer spatially multiplexed user. If we look at the analysis, we can see those different things. We see here the spectrum with the 3 different sections of users. This one is a beamform signal, minus 60 degrees to the direction. This is the spatially multiplexed signal with 4 layers, and then we have a plus 30 degree user in the scenario. We see the constellation diagram with all of the different users together. And down here, we see the composite beam pattern resulting from those users. Now, since we only have 4 elements in this simulation, the beam pattern is quite broad, but if we had more elements, obviously, we would have a more narrow beam pattern that you might be expecting. In any case, we see the minus 60 degree user here. That's why we have a big main lobe there. We also have the plus 30 degree user, which is showing up as red. And then we see some of the side lobes coming through. And then we have this middle section, which is the synchronization and broadcast signals, which had no specific gain and phase weights. They were all 0, so that makes a beam straight ahead. If you look at the beam weights, we can see the beam weights for each of those users. So we have the minus 60 degree direction, the plus 30 degree direction, and then in the middle, we see the gain and phase weights for the 4-layer spatially multiplexed user. Now, the interesting thing here is that I added an amplitude decrease for each of the increasing layers, and we can see what that does in our analysis. As the power goes down, the signal is closer to the noise floor, and that's making the EVM worse because the signal-to-noise ratio is going down. If we look at the frame summary by channel, we see each of the 4 layers there. The EVM starts out at 0.3%, then goes to 0.4%, 0.5%, and then ends up at 0.8%. If we look at the EVM as a function of subcarrier, we see the 2 single-layer signals that are beamformed have a very low EVM, but because of the decreased amplitude on the spatially multiplexed signal, we see the EVM there is higher. Now, if I take that beam pattern and I spin it around so we can kind of take a look at the back, we can see that the 4-layer spatially multiplexed signal has a spherical sort of antenna pattern. That's because we assume we're basically showing the antenna pattern per layer, assuming that we have an isotropic element. But we see 4 shells there of the power of that or the spatially multiplexed signal because of the decreasing amplitude. So that's pretty interesting. So there's a lot of different insights one can get from this analysis, and I've just given you just a couple of those. Over here in this setup is our high-performance generator and analyzer. So we'd say this is sort of a mid-range setup, and then we have high performance. Here, this instrument covers FR1, FR2, FR3, and even all the way up to 110 gigahertz. This particular unit has 2 channels, so we're using that to generate a 2-layer spatially multiplexed signal along with 2 additional single-layer signals. We see that in the spectrum here. This is the 2-layer signal. We have the single-layer signal and another single-layer signal. Each of those is coming out of a different antenna port. All right, so if you look at the orange user here, or the orange part of the constellation, we see that it doesn't look quite correct. The reason for that is because the data is overlapping and interfering with each other. Since we're combining both layers onto a single channel, it's causing that. Normally, if you wanted to demodulate the data from each layer, you'd need a separate channel. But many important cross-channel measurements can be made with a single channel analyzer like this. So even though we can't demodulate the data portion, we can still demodulate the demodulation reference signals or pilot signals, and we can see the EVM of those, and more importantly, the time alignment between them, which is very important to understand, as well as the power that is being generated there. So this is just a quick example of some of the measurements we can do. So we have mid-range, high performance. If you have any questions, feel free to visit keysight.com. Thanks for watching.